So today I will talk about theorem of Menelaus. Menelaus, Greek mathematician, lived in the 1st century in Alexandria. It's a simple theorem. It's a theorem of a theorem with enormous applications, and all that because in my opinion it's a wide and very flexible and very useful generalization of the theorem of Thales. It goes as follows. Now, I would like to write, okay, so theorem, I would like to write down a statement, theorem. So it's all about a triangle. Given any triangle, ABC, and points X. Well, I would like to take X on the side BC. So BC is the line, not the line segment. Okay, so it's keep an open mind as regards the position of X, but not so open-minded. You will exclude the possibility of X hitting one of the vertices. Okay, and Y, similarly, in cyclic fashion, now I can write on the side CA, with the exception of the vertices C and A. And finally, Z, so you have taken 3 points on the side AB. And once again, you exclude the possibility of Z coinciding with any of AB. So given this, in order for the points XYZ to be collinear, it is necessary and sufficient. Necessary and sufficient that the following relation holds, numerical relation holds, that it's necessary and sufficient that, here it is, XB, so the ratio in which X divides the line segment. Let me remind you, XB to XC, as I amply indicated in my introductory lecture, is a signed quantity. It can be positive or negative, depending on whether XB and XC are looking in the same direction. That's to say, of course, when X lies outside the line segments BC, then XB and C look in the same direction, and this quantity is positive. Whereas if X lies between B and C, then XB and XC look in different direction, and this quantity is a negative quantity, okay? So I gave the definition using vectors, so on and so forth. You will remember it. I made a big deal. It is a big deal. Okay, so, and then YC, YA, finally ZA, ZB. This will be 1. And, well, for reasons which will become clear, I make again a big deal of the fact that this is +1, okay? I mean, right, so that's the numerical relation. That's the numerical relation, which is, according to this theorem, necessary, not only necessary, but also it is sufficient for the 3 points X, Y, Z taken on respective sides BC, CA, and AB of the triangle. None of these are supposed to be coinciding with the vertices. This condition of coinciding with the vertices is not merely a technical thing. Of course, technically, if X hits one of B and C, this thing becomes ill-defined. So that's why, essentially, you do that. You prohibit the possibility of X coinciding with any of B, C. But it's also revealing, it's also important from different points of view. If time permits, I shall give some examples. Okay, so the thing looks like this. Okay, so let's take. Let me take. Let me consult my notes, like all bad teachers do. Okay, so here is the triangle. And okay, as usual, you make a point of it that the sides are infinite. Okay, and as usual, A, B, C. Okay, so here is your X on the side BC, not coinciding with B and C. And let's say Y, like this. And let's say, for the moment, let's imagine that X, Y, and Z are indeed collinear, so that's where Z is. Okay? So let's assume that X, Y, and Z are indeed collinear. Now, okay, so if, okay, so part one, if X, Y, Z are collinear, well, if you wish, you might like to start our proof here. Okay, so suppose that X, Y, Z are collinear. If X, Y, Z are collinear, then let me, okay, so there is a line containing X, Y, and Z, and to that line I draw a parallel through B, and I wanted to intersect the opposite side, CA, in a point T, okay? Well, this is, okay, so choose T on CA with BT parallel to the line YZ. Okay, so, I mean, ask yourselves, I mean, is this always possible? Is this always, I mean, possible? I mean, couldn't we perhaps have something like BT? I mean, couldn't we have something when we draw the parallel through B to this line that it just doesn't intersect CA? Could it be possible? Well, think about that. And I think that also is quite, okay, yeah. So we obtain, besides, we note that T is not Y, which is rather obvious. Okay, T is not Y because Z is not B. Okay, so now notice the following. Okay, so let's look at this numerical object. And I would like to prove that it's +1. Okay, so let me go ahead to do it. XB divided by XC times YC by YA, ZA, ZB. Okay, so what happens? XB by XC, well, is exactly XB by XC, since YZ and TB are parallel. XB to XC is exactly, so I can replace this object by xb to xc, yt to yc, to yc. And, well, let me leave this as it is, ya. And finally, za to zb. Well, za to zb, well, it's quite obviously ya to yt. Well, there we are. Well, things cancel out. Of course, the more astute among you will notice that this is not ordinary canceling out, but they do go away. Okay, so that's it. So that's it. So we have found that if x, y, z are collinear, then this quantity must actually reduce to 1. And indeed, for reasons to become clear, I make it a big deal to point out that it is plus 1. Right. Okay, so how about the converse? Is the converse true? The converse, so let me go back for the converse, go back to this part of the blackboard, the converse. As usual, this is the not so pretty part of the proof. I mean, it depends on what you consider pretty, of course. So let's assume that let's assume that we do not know. Let's assume that we don't know whether x, y, z are on a line. So let me draw for you a rather exaggeratedly incorrect picture, so that x, y, z are like this. I don't know whether x, z, y lie on a line or not. I don't know a priori. Now, you can join x and z. So, okay. So you can join x and z and let that line intersect the side CA in a point. Let me call it y prime. Okay, so let the converse, let xz intersect CA and y prime. And once again, ask yourself, is this possible? And what happens if xz actually does not intersect CA? That's what happens if xz is actually parallel to CA? Does it make sense or what? Well, if that happens, then x, z, and y prime are collinear. So by the first part tells me that in fact the ratio of xp to xc times yc to ya, I'm sorry, y prime c to y prime a times za to zb must be 1. Okay, so I think I've got I ought to have warned you about something. Okay, so we are doing the converse. What was the first part? The first part said that if x, y, z are collinear, then this numerical relation holds. Now I'm doing the converse. That means I assume that this numerical relation holds, so I shall prove that x, y, z are collinear. Okay? So since this is, okay, so if x, z, and y prime are collinear, so that this quantity is plus 1 by the first part. But on the other hand, I know that this is also equal to xb to xc, yc to ya, and that is true because of our hypothesis. So I'm assuming that this quantity is 1. So if you look at these two things, you can cancel out za over zb, xp over xc, which leaves you with y prime c, y prime a, and on the left, y c, y a on the right. That means the points y and y prime, divide the line segment CA in the very same ratio. There's only one way of doing it. There's only one way of doing it. Y must coincide with y prime. Hence, since you know that xz y prime, x, z, y prime, which is also y, are collinear. Okay, so there we are. So that's how it works. Çocuklar, people, ladies and gentlemen, it is very important that this theorem should be used backwards and forwards. It's a necessary and sufficient condition. And that it's a necessary and sufficient condition will be of vital importance. I shall show you examples in which you shall make use of the theorem of Menelaus to obtain certain numerical results, and you will put those numerical results to obtain a geometric result concerning the collinearity of something. But that is going to happen in my next lecture, I being presently badly affected by this cold in the head. I shall just give one example. And that's a very boring example, I am afraid. It's a very classical standard example, and let it be sufficient for this lecture. Example. It is, as I say, a classical example. Well, let me just explain on the configuration. Let's take a triangle and circumcircle. So I take a small one because you will see in a minute why. So that is, yeah, okay, something like this. A small triangle with its circle. And if you do the following, if you let the tangent to the circumcircle at the vertex A intersect, okay, so it's something like this, intersect the opposite side, that's say the side BC, in X. Okay? And if you let, similarly, the tangent at B to the circumcircle, if you let it intersect the opposite side, that's CA in Y. And finally, if you let the tangent at C, if you let it intersect the opposite side in Z, then, well, I have not got it quite right, but let me do a bit of correction. Okay, then you will find that, okay, so let me use a little bit of color to liven things up as usual. Okay, so here's my triangle, ABC. And here are the tangent lines. Okay, I mean that's something you have to be very careful about because it's a highly unstable configuration, and then perhaps something like this. Okay, so that. Okay, so. Well, each tangent intersects the opposite side. Well, the tangent at C intersects the opposite side, AB and Z. the tangent at A intersects the opposite side BC in X, and finally the tangent at why do I insist on? Okay. The tangent line at B intersects the opposite side CA in Y, and we claim that, as you have got roughly, we claim that, okay, X, Y, Z are collinear. So these 3 lines, these 3 points, I'm sorry, these 3 points lie on a line. Okay, so it's a classical example, so X, Y, Z as described. So X is the point in which the tangent to the circumcircle at A intersects the opposite side BC, and similarly you define Y and Z are collinear. Now why is that? Well, here's a typical game in your geometry of the triangle. Well, all you have to do is to observe the following. If you take, okay, so let me draw a slightly larger picture. That's, my circles tend to get a little pear-shaped as I, okay, right. Okay, here is the thing. Okay, so that's A, and the tangent at A intersects the opposite side in X. So what happens? Oh, okay, so, well, of course, your reaction is to compute the ratio XB to XC. Well, that can be done by simply noticing that this angle, so the angle between the tangent line and a chord is, exactly the same as the angle subtended by that chord at any point on the circumference, in particular at C. So these 2 angles are the same. So from that, you get the fact that the triangle AXB, AXB is similar. That's to the triangle. In fact, CXA. So that's slightly, it's somewhat tricky, but it's there. Okay, so you come to the conclusion that if you want, if not XB to XC, but its absolute value, or let's say the lengths, XB to XC, I'm sorry, let's look at XB to XA first. Okay, so the lengths XB to XA is exactly the same as AB. Well, that's obvious, AB to AC. And of course, this is equal to, yeah, well, XA to XC, which, okay, so if you multiply these 2 things, that means if you square this thing, you get the unexpected object, XB to XC must be the square of this object. So it is, so by the way, let's call this C, this is the length small c, this is the length small b, so it is in fact c squared over b squared. Well, the point X being on a tangent line to a circle must lie outside the circle, and of course X must lie outside BC. So in fact, this can be written as XB over XC, and we have found that it is in fact c squared over b squared. Do I have to insult your intelligence by computing YC over YA, going through this going through this whole detail? No. In a triangle, you can do everything. If you have chosen your notation correctly, do the cyclic thing. So I replace X with Y. So I replace C with A. And of course, you can check it. You can check it easily. And A with B. And of course, now you apply Menelaus. Menelaus. Of course, so this is telling me that if you multiply these three quantities, the result will be 1. And I'm making a big deal out of it for reasons to become clear, plus 1. So the theorem of Menelaus says that since this numerical relation holds, then the points x, y, and z must be collinear. This, Jupiter, is a very classical and admittedly somewhat boring example. In my next lecture, I shall try to give some more exciting examples. And I think it's a good point to stop.